This is a video tutorial explaining the rate law of a chemical reaction. First of all, the rate law expresses the relationship between the rate of a chemical reaction and the concentration of reactants. So, for example, if I have a chemical reaction of A plus B giving AB, now let's say we have 3A and 2B. So here's the formula. Now, what would be the rate law of this reaction? The rate law is a formula R equal K, which is called the rate constant, multiplied by the concentration of A raised to a certain order. The order is a number, an integer from 0 to infinity, 1, 2, 3, 0, 1, 2, 3, 4, whatever. So raised to an order of, let's say, a number n, multiplied by B, concentration of reactant B, raised to the order of another number. So again, N and M are orders, and the number of N and M can be from 0, 1, 2, etc. Now, the number N and M has nothing to do with the stoichiometric coefficients written on the equation. What I mean by this, here we see 3 next to A. It doesn't mean that N is equal to 3. And I see number 2 written next to B. It doesn't mean that M is equal to 2. So the orders I call N and M orders are not related to the stoichiometric coefficients of the reaction. Now, something that you should know about the orders. So for example, here's a reaction, 3NO giving N2O and NO2. When writing the rate law, or if the rate law of this reaction is given, it will not include the products. So here they gave us that the rate law is equal to K, the rate constant, multiplied by the concentration of NO raised to the power of 2. This means that this reaction is the second order in NO and second order overall, since NO is the only reactant. Another example. This is a reaction of NO2 plus CO giving NO and CO2. Now this is given. The rate law of this one is K multiplied by NO2 squared. Of course, the products are not included in the rate law. Now, when I look at this constant, at this formula, I see NO2 raised to the power 2, and I don't see CO written next to it. Now, CO is 0 order because anything to the power of 0 is equal to 1. Therefore, when this rate order is written and you do not see CO next to it, it means that CO is there, but simply the order of CO is 0. And since there is number 2, power 2 next to the concentration of NO2, it means that this is second order in NO2. Now, 2 plus 0 equal 2, so this reaction is second order overall. And so on. Another rate order example, another rate law example. This is R equal to K multiplied by NO2 squared. So this is second order in NO2 and second order overall. Again, I repeat, the order here has nothing to do with the number here. And here's the last example. R equal K multiplied by the concentration of H2O2. If there is no number, it means this is first order to the power of 1. So that's a first order in H2O2 and first order overall. Now, how do we predict the unit of the rate constant in the formula of rate law? We need to look at the overall order of the reaction. So if the reaction is 0 overall order, which means R equal K, K here will take the unit of R, which is the molarity per time. The time could be in seconds, in minutes, in hours, days. So it's molar per time, or time minus 1. So if I remove this, it's time minus 1. Again, the time could be saying seconds or minutes. Now, if the reaction is first order, R is going to be equal to K multiplied by the concentration of a reactant raised to the power 1. Here at this point, the unit of K is simply per time. So, for example, S minus 1 or minute minus 1 if the time is in minutes. Now, if it's second order, we start saying molarity minus 1, time minus 1. The time is not going to change. It's always per time. So, for example, molar per minute. So, M is to the power of 1, meaning that the reaction is second order. The reaction is third order, therefore M molarity negative 2 per time. So for example, M squared per second. If the reaction is fourth order, again the unit of K is going to be here fourth, so I write minus 3, S minus 1. Fifth order, the unit of K is M minus to the power of minus 4, second minus 1, or as I'm telling you, minutes minus 1. So it's always whatever order I have, I do it one number less and I put minus of that number. Now moving on, let's give some examples. I have here a given rate law of a certain reaction. Again, the rate law formula does not include the concentration of products. It's only for the reactants. Now, since I see here 3, that's a third order. So the unit of K is going to be M3. Okay, then this is minus 2, second minus 1. Now, another example. If there is no number next to O2, it means that this is first order. 1 plus 2 equals 3. This is a third order overall. So the unit of K is going to be M minus 2 seconds minus 1. Another example. Here's a rate law to the power of 1. So it's just per time minus 1 per time, the unit of K. If the time is in minutes, we say minutes minus 1, or per minutes, or per seconds, S minus 1. Another example, second order, it's M minus 1, S minus 1. And finally, the last example, if I don't see a number, that's a first order. So this is third order overall. And the unit of the rate law constant K is M minus 2, S minus 1. Now let's take some other examples, questions to solve. Consider the following reaction: X plus Z gives P. The rate law is given here and it says K multiplied by X and Z, meaning it's a first order in X and a first order in Z and a second order over all. So the unit of K is going to be M minus 1 and the time minus 1. Now, sometimes they ask you to write the rate law of a chemical reaction at a given temperature. So we read and we just apply the formula. W plus R gives Q. Q will not be included in the formula of the rate law. So the rate law is going to be K multiplied by the concentration of W to a certain order multiplied by the concentration of R to a certain other order. Now the question is saying it's second order in W, meaning that N is 2, and the zero order in R, meaning that M is 0. Now, since anything to the power of 0 equal to 1, finally, the final rate law formula in this question is R equal K multiplied by concentration W to the power of 2. Another example, write the rate law of the reaction A giving BB. Again, this one will not be included in the formula of the rate law. It's simply K multiplied by A to a certain order. Now the question is saying it's third order in A. So N is 3. And the question is directing you and telling you that B, of course, is not going to be part of this formula because it's a product. Another final question. This reaction, I will write R, rate law, equal to K, the rate law constant, multiplied by the concentration of NO raised to a certain power and the concentration of O2 raised to another power. It's first order in O2. It's first order in O2 and third order overall, meaning that n plus 1 equals 3. Therefore, n is second order. So here's the final formula of the rate law of this reaction. Now, let's take a different question. Consider the following information. This will not be included in the formula of the rate law because it's a product. Now it's saying the reaction is first order with respect to N2 and first order with respect to O2. So here's the formula of the rate law. First order with respect to N, first order with respect to O2. Now the specific rate constant K, this one is equal to 2.6 times 10 to the power negative 2. Now the question is saying if N concentration, N2 concentration is 0.5 to the power of 1 multiplied by the concentration of O2, which is 0.50 to the power of 1, what would be the rate R? What would be R of this reaction? So we multiply and we get the answer. And the final answer is going to be 3.25 times 10 to the power negative 3 molar per second. That's the unit of the rate law. Some random questions that can help you practice. This is a rate law given. Obviously, N is not in the formula, meaning that N has an order of 0. So the order with respect to N, because N is not in the formula, it's 0. If they asked about M, M is to the power of 1, first order in M. Another question. Here's a given rate law. What is the overall order? So this is power order of 2 and order of 1. It's third order overall. Now, before moving on to the method of initial rates that help you to find the rate law through an experiment, through experimental data, we need to understand the effect of changing a concentration on the rate of a chemical reaction. So, if a reaction is first order, let's say R equal K, A to the power of 1. What would happen to the rate of this reaction is if A is doubled or tripled or halved, whatever change I do to A. So if A is doubled, we say 2 to the power of 1 equal to rate will double. If A is tripled, so I say 3 to the power of the order of A. 3 to the power of 1 is 3. So the rate will triple. If A is halved, so I say half to the power of 1 equal half. So the rate will decrease by half. So the rate will be halved. So, in conclusion, if a reaction is a first order in a certain concentration, whatever change you do to that concentration, it will do the same to the rate law. a concentration doubled, rate will double. Tripled, rate will triple. Quadrupled, rate will quadruple. If it's divided by 3, the rate will decrease 3 times. Now, it's not the same case if a reaction is second order in a certain concentration. So here's the deal. R equal K multiplied by A second order. If I double A, so I say 2 to the power of 2, it's 4. So the rate will quadruple. It will increase 4 times. Now, if the concentration of A is tripled, 3 squared is equal to 9. The rate will increase 9 times. Now, if A is halved, so I say half squared, the rate will be decreasing 4 times. So the rate will decrease by 4 times. Now, one more example. If the rate law is third order in a certain concentration, so A to the power of 3, third order. If I double the A, if I triple the A, if I half the A, what will happen? So every time, whatever I do, I raise it to the same order. So this one will be equal to 8. So the rate will increase 8 times. If it is tripled, the rate will increase 27 times. If it is halved, the rate will decrease 8 times. Now here's another question. Consider the reaction W plus V gives Y. Write the rate law of this reaction. It's saying, of course, Y is out. It's going to be R to the power of W to a certain order N and V to a certain order M. Now it's second order in W. Second order in W. And first order in V. So first order in V. So here's the final rate law formula. Now determine the overall order. 2 plus 1 equals 3. This is a third order overall. Now what's going to happen if V is halved? Where is V? V is to the first order. Whatever you do, the change is the same. V is halved, rate will be halved. Because V is first order. So for half to the power of 1 equal half. If the concentration of W is tripled, now W is second order. So you say 2 to the power of 3. So the rate will increase 8 times. Rate will. Sorry, if it's tripled, I did the opposite. So if it's tripled, the rate will increase 9 times because you multiply 3, you say 3 to the power of second order will increase 9 times. If V is tripled, V is first order, rate will triple. Now, after understanding the effect of concentration, the change in concentration on the on the rate law, now we can move on to the method. Wait, I'll give you one more example and then I will move on to the method of initial rates. So here's another reaction. These two are out. I have a rate law which will include the concentration of X to a certain power, the concentration of Y to a certain power order, and the concentration of Z to another order. Let's say A. Now never forget K, the rate constant in the formula. X doubled, rate increases by a factor of 4. Doubled, increased by a factor of 4. So I will say 2 to what power gives me 4? It's the second order. So n is equal to 2. 2 squared is equal to 4. So this one is 2. Second order in X. Now, initial concentration of Y was doubled. Rate is doubled. It's the same. So Y is first order, because when I double to a certain power and I get the same number, it means that this power is first order. So M is first. Now for the third one, Z was doubled. No change. So I double, Z is to the power of A, I get no change. It means that it's zero order, no change. And here's the final rate law formula. So the rate law formula, R equal K multiplied by X to the order of 2, Y to the order of 1. And I can just skip Z because it's order 0. Deduce the overall order of the reaction. 2 plus 1 is 3. Third order overall. Now sometimes they might ask you questions to substitute and find the rate of the reaction. Find either R or either K. So it was found that for a certain reaction, the value of the specific rate constant K is 2 times 10 to the power negative 3 M2 M minus 2 S minus 1. From the unit, I can understand that this reaction is third order. Now calculate the rate of the reaction when the concentration of each reactant is 0.2. So let's substitute in the formula. R equal, this is the formula. K is 2.0 times 10 to the power negative 3 multiplied by X. Now the concentration is given to me 0.200 squared, and the concentration of Y is as well 0 squared. Here's to the power of 1. I plug that into my calculator and I find the answer. The final answer is 8 times 10 to the power negative 3. What's the unit of the rate law? Molar per second. Now we're ready to learn the method of initial rates. The method of initial rates will help you to determine the rate law of a reaction, A, B, for example, through experimental data. So how can I analyze this data? So there's a chemical reaction here, carbon monoxide, CO plus Cl2 giving CoCl2. So the reactants here are CO raised to a certain power that I don't know yet, and Cl2. How do I do this? How do I use this table? So first we work each reactant alone. So the question here is directing you to start and finding the order with respect to CO. So now I need to find N. I choose 2 trials where the concentration of CO is changing. This is 0.120 and this is 0.060. I can choose trial 1 and 2 because the concentration of CO is changing, or I can choose 1 and 3, or 2 and 3, or 3 and 4. However, it's not just that the condition. If I am finding the order of CO, I must also select the same trials where Cl2 concentration did not change. So I need a change in CO and I need Cl2 concentration to be constant. So if I took trial 1 and trial 2, the concentration of Cl2 remains constant. So I'm going to choose trial 1 and 2 to make Cl2, keep it constant, and see how the change in the concentration of CO affecting R, the initial rate of this reaction. Now, to make this easy, always follow the number. Now, this is a larger number, this is a smaller number. So you always divide the larger by the smaller. 0.120 over 0.60 and raise it to the order n. I'm finding n. So I'll raise it to the order of n equal. Now, what did I do? I said trial 1 divided by trial 2. So I take rate of 1 divided by rate of trial 2. And I plug it into my calculator and I find the answer. So here, this is 2 to the power of n equals 2. So n is equal to 1. So the first order of CO, the order of with respect to CO is 1. So now let's change it because now we know it. It's first order. Now it's the time to analyze the order of Cl2. So again, we choose two trials where Cl2 changed, but CO remained constant. Now, I will take those two trials. I'm gonna move away from trial 1 and trial 4 because I don't know. I don't have the initial rate. There's an unknown. So let's stick to trial 2 and 3 or 1 and 3. 2 and 3. This one where the concentration of Cl2 changed and the concentration of CO remained constant. So trials 2 and 3. As I told you, you take the larger number divided by the smaller number. So 0.400 over 0.200 raised to the order of Cl2, m, is equal to, I started 0.4 over 0.2, so in the R rate law I say 4.0 times 10 negative 3 divided by 1 times 10 negative 3. So the answer here is going to be 2 raised to the power of m equal to 4. What should be the order m? M is equal to 2. So now I know that it is second order with respect to Cl2. And here's the final formula of the rate law. First order in CO, second order in Cl2. Now, expect always a question after finding the rate law formula to ask you to calculate K. Calculate the specific rate constant of this reaction. Here, you can choose any trial 1, 2, or 3, not the 4, because I don't have R. So I need any of those trials, 1, 2, or 3, in order to substitute and calculate K. So let's say I'm going to take trial 1. R is equal. Now in the table, let me just write the value of R from the table. It's 2 times 10 to the power negative 3. 2 times 10 to the power negative 3. K. Now, what is the concentration of CO in this trial? It's 0.120 and CO is first order, and the concentration of Cl2 in this reaction is 0.200 second order. I substitute and I finally find K, which is going to be 4.16 times 10 to the power negative 1. Now the unit, never forget a unit. This is a third order overall, so the unit of K is m minus 2. Now here we're dealing with seconds, so I'll say s minus 1. Now, here, after having all the unknowns, after having K, we just need to find R in trial 4. So this is trial 4, and I need to find R. Now having K, having the concentration of CO in trial 4 to be 1.120 raised to the first order of CO, having the concentration of Cl2 0.400 squared, I can find the final answer, the rate law of this reaction. The rate of this reaction is 1.6 times 10 to the power negative 1. One final question, one final example. Here's another reaction where we need to find the rate with respect to NO and the rate with respect to Cl2. So let's start with NO. So I'm gonna write a formula of the rate law, assuming now that the order of NO is N, we don't know it yet. The rate order of Cl2 is M, we don't know it yet. Now, to start with NO, I select two trials where Cl2 is constant and NO is changing. So that means trials 1 and 2. You always divide the larger number by the smaller number. It makes the calculations much easier. So I'm calculating the order of O, so it's the power of N. I divided the concentration of NO in trial 1 over the concentration of NO in trial 2. So I'll do the same in R. So 3.2 times 10 to the power negative 4 over 8 times 10 to the power negative 5. So plugging this into my calculator, this is equal to 2 to the power of N equals 3.2 times 10 negative 4 over 8 times 10 to the power negative 5 equal to 4. So the order is second order with respect to NO. Second order. Now it's time for Cl2. I'm gonna take two concentrations, two trials where NO is constant and Cl2 is changing. So that means trials 2 and 3. The higher number divided by the smaller number. So 0.0800 over 0.0200 to the power of order of Cl2 that we don't know yet. Now I started trial 3 over trial 2. So initial rate of trial 3 over the one of trial 2. So again, that's a 4 equals to the power of M equals 3.2 to the power of negative 4 over 8 to the power of negative 5 equals to 4. 4 to the power of what equals 4? Meaning M is 1. And now I know that Cl2 is first order. This reaction is first order with respect to Cl2. So now let's write the final formula of the rate law. It's second order with respect to NO and first order with respect to Cl2. Oh, sorry, I have to write this one over here. KNO squared and Cl2 to the power of 1. And this reaction overall order is third. 2 plus 1 equal 3, third overall order. Now calculate the specific rate constant. That means K of the above reaction. So I can take any trial that I want. So let's say I took trial 1. R in trial 1 is 3.2 times 10 to the power negative 4. I'm substituting in this formula. It's equal to K multiplied by the concentration of NO 0.0350 squared multiplied by the concentration of Cl2 0.02 first. Plugging this into my calculator, my final answer, the rate law constant is going to be 13.06. Now the unit, what's the unit of K? Third order, K is m minus 2. Let me check. Here we're dealing with seconds, s minus 1. And that's it. Thank you for listening.